Okay, so now we're going to pick right back up on where we left off. So if you would like to have a recap of different kinds of memory concepts, the subprocesses of memory, things like that, please go back to part 1 and watch that. So we're going to pick right back up, and this is a little bit more specific, a little bit more detailed. So if you haven't had, a neuroscience lesson in a while, I encourage you to do a little bit of review prior to. So when we talk about non-REM, especially with slow wave sleep, we know that is a important type of sleep that's going to play a pretty significant role in consolidation. We also know that REM is important, but it's actually seems to be more important for things like emotional memory as well as creativity. There's also some evidence about non-declarative memory, but I don't want to go into that particularly in this lecture. Now, we're going to talk about some key EEG features. One is the slow oscillations, or SOs. We're going to talk about spindles, and we're going to talk about a new oscillation or feature that we haven't really gotten into yet, and that's ripples. And so these are really, really interesting because of the way they kind of nest into the spindles. And so this gives us some evidence for potentially what might be going on and how this kind of creates this kind of replay loop to allow for consolidation to occur. So a lot of this is just kind of the systems repeating and replaying themselves in order to establish some kind of system that is strengthened. Now, I pulled this particular image from a paper by Zhang, and it was published in 2019, and this is available on Blackboard for you guys to check out. I thought it was a really good representation of some of the things that are happening, and so I'm going to kind of walk through this because it's, in my opinion, a really good kind of demonstration of what's happening. So when we talk about upstates, so here we have upstates and we have something called a downstate. And this is where we see that kind of blue is a downstate and the up is an upstate. So when it comes to upstates are where we see depolarizations in the neurons. So this is essentially a high neuronal firing period of time, okay? And we refer to these as upstates. Now, downstates are kind of the opposite of that. This is where we see kind of a quiet periods where we see hyperpolarizations. And this is where we're going to see not as much activity. So these are referred to as upstates and downstates. Now, typically when we see this happen in an EEG, okay, we're looking at specifically a slow oscillation. So like less than 1 hertz, that would be this whole oscillation right here. I'm just going to kind of show it right there. That's this whole oscillation of 1 hertz. Think of slow wave, delta wave sleep, right? And these are where we see these kind of organizations of upstates and downstates. Now, we've talked about spindles before. We've talked about spindles and K complexes in relation to sort of being a mechanism to kind of keep you asleep. So if there's a noise or something that's just loud enough for you to register but not loud enough to wake you up, we typically will see something like a spindle and a K complex, but we've also seen it implicated in learning and memory. So we're going to kind of pause what we know about this in terms of keeping you asleep and potentially being like almost like a filter within a filter. We are going to focus more so on the memory component today. So these spindles are these 12 to 16 hertz kind of big, you can see this here, okay, this spindle right here in the red, okay. These are thalamocortical features, and we think that they might be linked to the strength of your learning that takes place. So more of these could indicate better learning, stronger learning, things like that. And then so these spindles are housed within the wave. Okay, these are within the slow oscillation. All right, and then we see, and this is specifically in the hippocampus, so this is looking at how the hippocampus is generating these oscillations and then communicating with the cortex, okay, which will come to play in just a minute here. These ripples then, so the the sleep spindles are nestled within the slow wave, and then the ripples will nestle within the spindles. And so it's kind of like this idea where they're nesting inside of themselves, okay? And so potentially that could be driving the replay information. And I'm going to explain that on the about 2 slides from here. So, important thing to remember here is that these ripples are nested, and these are specifically hippocampal. So this is HC, posterior and anterior hippocampus, right? These are accompanying this memory replay. They're nesting inside of the spindle, which is nesting inside of the slow wave oscillation, okay? Now, one important factor here, okay? The memory consolidation relies on this conversation here between the hippocampus and the cortex. So that we call this the dialogue, right? This conversation between the hippocampus and the cortex is important in this memory consolidation process, because we know that it kind of begins in the hippocampus and then it has to kind of translate that information out to the cortex. These reactivations, these replays that the hippocampal neurons are doing during non-REM sleep are potentially what's causing these memories to concrete and then communicate to the cortex to concrete in the brain. And what drives this is those slow oscillations, the spindles, the ripples working together for the information transfer and the information replays in order for us to be able to have these memory systems do this consolidation process, okay? So if we look through this kind of again, so sort of kind of coming back into this, okay? So we have this conversation that the hippocampus is having with the cortex, okay? Now, if we look at the black arrow here, this is the cortex communicating to the hippocampus. So think about this. During your wakeful experience, right, you are encoding representations that are distributed all throughout your cortex, okay? And then that information will be encoded partially, right? Or that it will be encoded through your hippocampal networks, okay? And then that information of relational aspects of like when and where, okay, that is going to be communicated with this black arrow from the cortex to the to that hippocampus, okay? Now, during the sleep process, you're going to see this repeated neuronal replay of this newly encoded information, basically these hippocampal representations, right? During slow wave sleep, you're going to see this gradual transformation of these representations into more persistent semantic types of memory. And then this will then get distributed out to the cortex. So information to the hippocampus during wakefulness in terms of how you are encoding information, then the hippocampus will then distribute this information out during sleep in order for you to consolidate this information into concrete networks. So, and it does that through the nesting of the sleep spindles in those slow oscillations, and then the ripples within the spindles to help it replay and reactivate that information, okay? So when those ripples are nested within those sleep spindles, it's going to replay in those hippocampal networks, right? And it's going to excite those spindles, and it's going to then allow that information to be transferred and repeated, and so on and so forth. Now, what's very interesting is that we have some explanation through evidence as to how this could be happening. Now, I pulled this study, and this is on your Blackboard. I really, really like this study because it's a very kind of interesting take on what could be happening in the brain. Now, NPR did a write-up on this study. You can actually access the NPR article here, but you guys have this actual paper that was published in Neuron in 2015. It's the Foster et al. Paper. And what this is a really interesting study on what was happening in the brain, direct electrodes on the brain in humans. So you might go, wow, that seems kind of intense. And it is. And so before we jump into what happened in the study, I want us to talk a little bit about something called ECOG. So this is electrocorticography, which is essentially it's putting these electrodes directly on the brain surface. So here you can actually see that the person has had their skull remove the scalp, skull, meninges, everything removed, and this is exposed human brain right here. And you might go, well, why on earth would somebody do that? Well, in individuals who have epilepsy, if they're already undergoing brain surgery, sometimes researchers will go in and say, oh, hey, we're doing this study. Would you mind if we add on an experiment while you have this kind of exposed brain? And so typically what ends up happening is they need to have this exposed for a period of time, a couple of days or whatever, a day, so that they can have tests run, so that if they're going to have surgery on a specific part, let's say right here and around their temporal lobe, they may need to ensure that they don't damage anything. And so the person is going to have almost like a couple of surgeries, one to kind of take this off and then establish electrodes for the surgery, and then they're going to have that replaced. They're going to have this sort of temporarily put back on, and they're going to have their head wrapped, and they're going to be monitored for a couple of days, and then they're going to have the surgery. And so during this process, sometimes researchers can come in and ask, hey, can we run a study? And this is a really cool video of a brain surgery where a person was singing. And typically something like this is done where the person is awake. And so you don't want to accidentally cut an area of the brain that is very vital. Let's say if the person is a world-class opera singer, if they play the piano, if they play guitar, you would actually have them do those activities in the operating room and make sure that you're not actually cutting into tissue that could damage them. So of course they have it mapped out. They have all this, MRIs and the EEGs and everything done prior to make sure that they have a map of the brain, but they still want to make sure that they're not going to harm it. So they'll touch points first and say, did you lose function, or did did something weird happen here? And then they will then go in and do the surgery. So one thing to consider here, this particular ECOG study is on epilepsy patients. So is it generalizable? Possibly not, but it's also a very small study where they only had 4 participants, I believe. And so it's a small study, but we don't get a chance to do this very often because it's not often we get to put electrodes directly on the brain. So here, this particular study, it's 3 patients. I said 4. So it's 3 human epileptic patients. They used ECOG prior to the surgery that they were supposed to have for their epilepsy. They essentially looked at the medial and lateral parietal cortices to see if they were coordinated during certain activities. So they were asking them questions, basically episodic memory retrieval, like, did you drive to work today? Did you go here today? And obviously they went to the hospital to, have the surgery. So they were able to establish these very specific areas where the memory retrieval was happening. So they could kind of see it in real time. Okay, well, you're using these areas to think about these particular episodic memories. And then they observed the ECOG activity while the individuals were asleep. So they were looking at them during rest as well as sleep. And they found that coordinated activity that they saw when they were asking them episodic memory questions, during that retrieval, they saw that those activities were matched on pretty well in terms of the patterned activity. So one conclusion that they made from the study was that anything that you do during sleep is actually probably not random. It's probably something that is replayed from the day, and that's kind of that theory of this active systems consolidation theory. This is us kind of thinking, hey, you are essentially replaying your day while you sleep, deciding what memories to concrete, and then concrete those memories, and then get rid of everything else, right? Just delete all the stuff that you don't need. And when we start to talk about dreaming, which we'll get to at the end of the semester, we're going to talk about how cognitive scientists, some of them say, well, it might be that we just have random firing in the brain during sleep, and it's not as coordinated as we originally as this particular study, for example, shows. So this would actually disprove any theory that says that dreams and cortical activity during sleep is actually random firings. We know that through this Foster et al. Study and other studies that it's probably very coordinated activity, and that coordinated activity is actually coordinated with wakeful activity. And so this still begs a lot of question, right? There's still a lot of unresolved questions in sleep and memory. So first of all, how do we decide? How does our brain decide what memories to retain and which ones to forget? Now, sometimes we tend to remember that one thing that we would like to forget, and the thing just keeps replaying in our minds. Why is it that we choose that one? Why is our brain set on this one? Why can't we forget the things that we want to forget, which some people do? But, how does this selection process work? How does REM work in memory consolidation? We know that some people have very limited REM, or not much, not any at all. Does that affect their memory process? Yes, it does. But how does that still work when you have, a particular type of sleep that you don't experience in a typical fashion? Also, there's another question about how do the oscillations determine which synapses are modified. And this is a specific to another theory, and I kind of left this in because I thought this was really interesting, thinking about the balance and homeostasis in the brain. There's multiple theories about about the oscillations and about how memory works, and some of this is looks to modify certain synapses to strengthen them or to weaken them. And so how is it that the decision process is made that these particular synapses are going to be strengthened, and then these other synapses are going to be weakened? And we know that when you have strengthened synapses, obviously that's going to lead to recall or learning or memory of that particular function. So still a lot of questions that we don't have answers to, but we still continue to look through and do experiments that hopefully will provide us some more guidance. And hopefully this is helpful in understanding some of the mechanisms that are taking place with learning memory during sleep.